Welcome to the Explainer. I'm so incredibly thrilled to have you here today. Our goal for this breakdown is definitely ambitious, but it is deeply, deeply fascinating. We're going to completely demystify the core technology that's actually driving this entire modern AI revolution. And we're going to pry open the black box behind those tools you're probably using every single day.
Because it really feels a bit like magic, doesn't it? I mean, how exactly do these massive computational systems generate such incredibly human-like text? How do they understand complex, multi-step instructions, or hold conversations that feel utterly natural? We type in a quick prompt, and boom, a perfectly articulated essay or a complex block of code just appears out of nowhere. Well, today, we're stripping away that magic and taking a hard look at the actual engine under the hood.
So here is our roadmap for how we'll break this down. First, the AI revolution. Then we'll look at the older RNN models, unpack the massive attention breakthrough, dive deep inside the architecture itself, explore how the models are trained, and finally look at where all this tech is heading next. Let's get right into it.
Starting with Section 1, the AI revolution. And wow, what a rapid evolution it's been. The explosive speed of this AI evolution it's literally staggering. I mean, look at this timeline. We go from a single research paper published by Google in 2017 to the release of BERT and GPT-1 just a year later. By 2020, GPT-3 kicks off the era of these massive foundation models. Fast forward to today, and we're looking at unified, multimodal models like GPT-4o, Claude 4, and the GPT-5 family. We literally moved from a theoretical white paper to autonomous reasoning systems in less than a decade. That is wild.
Moving right along to Section 2, before transformers. The era of recurrent neural networks, or RNNs.
To understand the leap, you gotta understand the problem. Older RNN models had a really severe bottleneck. They processed data sequentially, so one word right after another. This meant they couldn't fully utilize modern GPUs for parallel computation, making training painfully slow. And worse, they suffered from this sort of amnesia. They seriously struggled to remember context from the beginning of a long paragraph by the time they reached the very end of it. Transformers? Totally different story. They process all the data in parallel. They are insanely fast to train on GPUs, and they maintain this deep, unwavering contextual awareness from start to finish.
Which brings us to Section 3. Attention is all you need. The massive 2017 breakthrough. Attention is all you need. You know, it's not just a catchy title. It was an absolute rebellion in computer science. This paper essentially proved that you don't need recurrence or sequential processing at all. A mathematical technique called attention is entirely sufficient to understand human language.
Okay, so what actually is self-attention? Well, it's a mechanism that lets a model relate every single word in a sequence to all the other words simultaneously. Think of it like being at a super crowded cocktail party. Even with dozens of different conversations happening around you, you can focus your attention entirely on the person speaking directly to you, right? But you're also subconsciously keeping track of someone calling your name from all the way across the room. Self-attention lets the AI know exactly which words in a sentence relate to each other, no matter how far apart they are structurally.
Let's dig deeper in Section 4, inside the architecture. Time to really open up the black box.
At its absolute core, the transformer is surprisingly elegant. It relies on a basic encoder-decoder structure. Now we've got to clearly separate these two distinct phases. The encoder is all about the understanding phase. It takes your input and builds a really rich mathematical representation of its context. Then, the decoder is the generating phase. It takes that understanding and auto-regressively produces the new output. That just means it predicts things one step at a time, like a translation or a chatbot typing out a response.
Let's see exactly how this understanding gets built step by step through the encoder workflow. First up, we have input embeddings. This simply turns our raw words into arrays of numbers, known as vectors. But since transformers don't read sequentially, we need step 2, positional encoding. This injects mathematical markers into those vectors so the model actually knows the original order of the words. Then, we hit the absolute heart of the machine in step 3, multi-headed self-attention, which scores the context. And finally, step 4 is a feed-forward network that refines all of this raw data into a highly polished, abstract representation.
Now, to gain a truly robust understanding, Step 3 uses what's called multi-headed self-attention. This breaks the data down into multiple parallel streams, or heads. Inside each head, the model assigns 3 distinct roles to every single word: a query, a key, and a value. When a query vector aligns perfectly with a key vector,
boom, the model gives it a high attention score, which basically means those words are highly relevant to each other. Doing this across multiple heads simultaneously gives the model an incredibly robust, multifaceted understanding of the text. It's like looking at a problem from 10 different angles at once.
All right, shifting gears over to the decoder phase. The system auto-regressively generates text token by token using the 4-step workflow you're seeing right here. It starts with its very own embeddings and positional encodings, moves through masked self-attention, integrates the encoder's data via cross-attention, and finally pushes it all through a linear classifier and a softmax layer. Now, softmax is basically just a mathematical filtering system used to calculate the exact probability of what the absolute best next word should be.
A totally vital part of that generating process is masked attention. While generating text, the decoder uses previous words to predict the next one. Masking effectively blinds the decoder to future tokens in the sequence. Basically, it stops the decoder from cheating by peeking at future words before it actually generates them. It forces the model to truly predict the sequence organically.
That brings us to Section 5, Pre-training and Fine-tuning. How do we actually teach this model to behave?
The contrast between these two phases is massive, and it's fundamentally how the entire AI industry operates today. Pre-training is where the model essentially learns the statistical rules of human language by reading massive amounts of raw internet data. It requires thousands of GPUs and millions of dollars. Fine-tuning happens afterward. It uses a much smaller set of highly curated, human-annotated data to teach the model how to actually be a helpful assistant, or a medical expert, or a software coder. Pre-training builds the foundational brain, fine-tuning shapes the specific behavior.
And, we really have to acknowledge the environmental and financial impact here. Training these base models requires just vast amounts of electricity. That's exactly why the open source movement, driven by platforms like Hugging Face, is so absolutely crucial. By sharing pre-trained model weights openly, developers worldwide can skip that massively expensive pre-training phase and jump straight into fine-tuning. It means the global community isn't endlessly burning energy to train base models from scratch over and over again.
Because of these incredible efficiencies in training and architecture, we're seeing some truly mind-bending capabilities. 200,000 modern models like Anthropic's Claude 3 can now maintain a massive context window of up to 200,000 tokens during a single conversation. To put that into perspective, that means you can literally feed an entire book into the prompt, and the model will hold all of that context in its active memory, using its attention mechanisms. No amnesia whatsoever.
Finally, let's wrap up with Section 6, the future of transformers. What exactly lies ahead?
Today, this landscape is dominated by a few major players. And transformers aren't just about text anymore. Vision transformers treat image patches exactly like words, and they're completely dominating image classification right now. Multimodal transformers are unifying text, audio, and video into single, massive computational brains. And efficient variants, they're using brilliant optimizations like flash attention to drastically reduce GPU memory usage, which is what allows for those massive context windows we literally just talked about.
But despite all this undeniable power, we really have to stay grounded. These systems have some serious limitations. The biggest one is quadratic complexity. Because every word must attend to every other word, doubling the input size actually quadruples the computational cost. It scales at O of n squared. It's an enormous bottleneck. Plus, we have to remember these models are supreme pattern matchers, but they lack explicit symbolic reasoning. This is exactly why they can confidently hallucinate facts. They're predicting the most statistically likely next word, not explicitly checking against a factual database of truth.
Which leaves us with a pretty profound realization. We're currently watching these models pivot right before our eyes. From being passive, conversational chatbots into active, autonomous agents capable of multi-step planning and executing actual real-world workflows. The technology is completely stepping out of the chat window. So my final question for you to ponder today is this. As transformers become the central reasoning engines for autonomous systems, what industry will they fundamentally dismantle and rebuild next? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I will see you next time.